The modern standard for AI computation is the NVIDIA H100 GPU, a piece of silicon engineered with strict theoretical limits on processing speed. For years, researchers have optimized standard autoregressive language models, systems like GPT-40 Mini or Claude Haiku, to push the boundaries of this hardware. Yet even with extreme optimization, these models hit a hard performance ceiling, tapping out at around 200 tokens generated per second. But a new class of models, known as diffusion language models, generate text through iterative denoising, unlocking new capabilities on this exact same hardware. This graph plots generation speed in tokens per second. The autoregressive baseline flatlines near 200, but diffusion models like Mercury Coder rocket to 1000. Notice the hardware. This 5-time speedup happens on standard NVIDIA H100s, not specialized chips. If the silicon processing the math is identical, something in the underlying structure of autoregressive models must be actively bottlenecking their performance. Generating text sequentially from left to right is mathematically mismatched with modern GPU architecture, forcing frontier labs to abandon it for iterative denoising. Autoregressive models operate on a strict mathematical objective, left to right next token prediction, like a typewriter. They must compute token n, finalize it, and then use that output to predict token n plus 1. To manage this context, they rely on a key value, or KV cache. The KV cache is a memory mechanism that stores the computed attention states of all previous tokens. So the model avoids recalculating the entire prefix for every new word. Generating a sequence requires moving this cache back and forth from the GPU's memory for every single token, creating a traffic jam in the memory bandwidth pipeline. Meanwhile, the actual math processors sit dark and idle. Generation speed becomes strictly locked to how fast data moves through that narrow memory pipe, regardless of the GPU's total computational tower. It is the equivalent of a massive factory floor of workers standing around waiting on a single, slow conveyor belt. Autoregressive models are memory-bound. They are structurally incapable of utilizing the massive mathematical horsepower of modern hardware. The alternative architecture is the Masked Diffusion Language Model, or MDLM. Instead of typing piece by piece, diffusion asks the model to reveal the entire structure at once, assembling it from a state of noise. A diffusion model begins its forward pass with a sequence composed entirely of pure noise or placeholder mask tokens. The model evaluates the entire noise sequence simultaneously. In a single forward pass, it predicts the underlying text for all positions at once. It then refines this output in iterative ways, progressively replacing uncertainty with highly probable words. Finalizing hundreds of tokens this way typically requires only a dozen or so total steps. By abandoning the left-to-right rule, diffusion replaces a sequential memory fetch with a massive parallel equation. This brings us back to the physical reality of the H100 chip. These GPUs are designed to maximize arithmetic intensity. They perform optimally when they are compute-bound, executing dense math operations rather than waiting on memory transfers. Because diffusion models process all tokens simultaneously, they completely bypass the need for a sequential KV cache. They swap that memory dependency for massive parallel matrix multiplications across the entire sequence length. This parallel processing perfectly aligns with the GPU's natural hardware profile, allowing the model to fully saturate the arithmetic cores. This is the exact mechanism that allows models like Mercury Coder to achieve over 1,000 tokens per second. This 1,000 token per second throughput stems from a native architectural match between the diffusion framework and high compute silicon. The architecture of diffusion models also changes how the system processes logic and reasoning. Autoregressive systems suffer from a structural vulnerability known as exposure bias. Exposure bias occurs when a model generates text based on its own potentially erroneous prior predictions, causing mistakes to compound. If an autoregressive model makes a minor logical error early on, it is locked into that error because its attention is masked strictly to the left. This causal masking prevents the model from looking ahead to correct itself, forcing it to justify the initial mistake. In contrast, a diffusion model utilizes bidirectional attention. Every token position can attend to both the left and the right simultaneously. This allows a token to cross-reference the end of a sentence to logically correct the beginning of the sentence mid-generation. This iterative self-correction acts as a built-in reasoning step, making diffusion models highly effective for complex logic, math, and code generation. Relinquishing left-to-right generation provides hardware speed, but also gives the model the ability to evaluate and revise its logic before committing to a final output. Zooming out from the chip architecture reveals a broader industry crisis: the exhaustion of high-quality human text. We are entering an era of data-constrained settings where research labs have effectively infinite compute but a strictly limited supply of unique training data. When an autoregressive model is forced to train on the same limited dataset repeatedly, its strict left-to-right factorization becomes a liability. It quickly reaches a point of overfitting. Instead of learning underlying concepts, the model simply memorizes the specific sequential patterns of the training text. These models suffer a rapid data half-life. Their performance plateaus and saturates after only about 15 passes or epochs over a dataset. To survive the data wall, labs have to find ways to extract more intelligence from a fixed number of tokens, rather than simply scaling compute. Masked diffusion models bypass this data limit through their randomized masking objective. Because the tokens are randomly masked during training, every single pass creates a completely new combinatorial puzzle for the model to solve, even if the underlying text is identical. Researchers call this phenomenon implicit data augmentation. This chart from recent NeurIPS research maps validation loss against compute. The autoregressive line flatlines at the 15 epoch mark, but the masked diffusion line smoothly drops past the autoregressive plateau, continuing to improve its validation loss consistently down to 500 epochs. This represents an orders of magnitude increase in data efficiency. By shattering the sequential memory bottleneck, enabling bidirectional error correction, and maximizing data efficiency, diffusion language models provide the architectural blueprint for the future of reasoning engines.